Usually when you start looking for friction coefficients, you will find a table very similar to this. We can see that when steel interacts with steel, we have a certain friction value. When ice slides on ice, we'll have a much lower friction value. So the question is, how do you define this in a physics simulation? Assume that we have two objects. One is made of rubber, and in AGX Dynamics for Unity, we use something called ShapeMaterial to define that material. And it also has a density. We create another shape material called steel, which has a much higher density. And to define the interaction between these two shape materials, we create a contact material. And this will build up a table with all the interaction between the different materials. So if we have a look once again, we have rubber, we have steel. We create the contact material and we associate the rubber and the steel. So when they collide, we know which friction coefficient that will be used. We use that table value for the restitution, the YoungsModulus, etc. If we introduce a third material like wood, we specify the density and we create a contact material. So at the end, you will have an interaction table like this, where some of the entries are filled and some are not filled. And when you don't have a value, for example here with steel, a default contact material will be created, but you don't know what friction value that will be used. It's some default value. So if you want to have full control, you have to fill out this table. If we create a box that we use for a ground plane, so we make it a really large box like this. Now we have a collision shape, which is a box that does not have a rigid body, which means that it will be considered to be a static collision shape. Next, we create a sphere. We just move it up a little bit. Now, if we start the simulation here, we have an initial state, which defines that this sphere is hovering above this plane. So if I start it, it should fall due to gravity. And we can see that it bounces a little bit. And that means there is some restitution here. We don't know much about what is the default friction, what is the default restitution, but there is some value. But we want to have full control of this. So the first thing we have to do is we have to define what material this shape is made of. And we can see here that we don't have a shape material. So either we can locate one or we can create a new one like this. So let's call this box shape material. We can see that this box shape material has a number of parameters, one of them being density, and that is the definition of the density of this object. So from the density and from the volume, if this shape is part of a rigid body, we will compute the mass from that. We also have things related to wire simulation, which we will bring up in a later session. Okay, so now we have a box made of a box-shaped material. Now we also need to define what kind of material this sphere is made of. So let's create another one and call that sphere shape material. So now we have this sphere shaped material. We use the same density in this case, so we don't have to change that. Now let's have a look at the rigid body, and we can see that it has computed a mass from this density and the volume of the sphere. If we would reduce the radius of the sphere, and we can also see that the mass has been updated because we changed the radius. Now if I would go and change the density of this sphere into something which is steel, we can also see that the mass is updated. So now we have a shape material for the box, and we have a shape material also for the sphere. But that doesn't mean that we have control over what happens when these two collide. We get exactly the same response as before. To control the exact behavior when the box shape material collides with something that has a sphere shape material, we need to create a contact material. So we can see that both the shape material and the contact material are actually assets on disk. Sphere, we call this sphere box contact material. So now when we have created a contact material, we can see the parameters that goes into a contact material. The two first are references to ShapeMaterials. So in our case, we're going to use the box shape material and the sphere shape material. The third one is FrictionModel. And here we can actually define what solver is going to be used and what algorithm for computing the friction will be used. We'll talk more about that later. YoungsModulus is the stiffness of the contact. As a reference, steel has a stiffness of 200 gigapascal. Surface viscosity, that's really the stiffness of the friction. We can use that to emulate sliding friction. For example, if you want to use a contact material for a tire on a car, you probably want to have some slippage in the orthogonal direction of the friction. So you have a forward direction and an orthogonal direction. To get some slippage in the sideway, you want to increase the surface viscosity. Friction, well, we can see as well as surface viscosity, it has two entries here. And one of them is the primary direction and the second one is the secondary direction. More about that later. If you just want to set the friction, set the same on both of them. Restitution is the bounciness or how much energy is being lost during an impact. If we set it to 0, we'll get no bounciness at all. If you set it to 1, it will keep bouncing forever. Damping is really a solver setting. It's the time that's being used for computing how fast a contact should be restored. It should always be 2 time steps. So please check your time step that you're currently using in the simulation and multiply that with 2. That should be the damping for your contact. Adhesive force and adhesive overlap, that's more to do with modeling suction or some kind of adhesive surface that stick together. Contact area, well, some of the contact colliders that we have can actually compute the contact area, so you will get a more accurate contact force calculation. I would recommend that you keep this checked. Contact reduction mode, that's very important. We'll talk more about that later, but it has to do with an algorithm for reducing the number of contacts when two things collide. Very important for mesh. And here we have 2 parameters for wire friction coefficients. I will talk more about them later on. Now there's a warning down here and it says the current scene doesn't contain a ContactMaterialManager, and it asks you to create such a ContactMaterialManager. So what we can do actually is click that or go up here in the manager and create the ContactMaterialManager. The reason we need a ContactMaterialManager is that we need a way to instantiate these assets into the scene. Because we can have hundreds of contact materials on disk, but that doesn't mean they are instantiated into the scene. So to actually use this contact material that we just created, we need to add it to the ContactMaterialManager. Because this manager is actually a part of the existing scene. It's being instantiated into the scene. So now we have a ContactMaterialManager. It has an entry of 1 contact material, which defines the interaction between a box shaped material and a sphere shaped material. And we can set the restitution to 0. And now we should see that the sphere doesn't bounce at all. If we change the restitution to 1, we will see that it just continues to bounce forever because no energy is being lost. We could even set it to 1.2, which means that it will actually gain energy every time it bounces. So it will bounce higher and higher and higher. Now, one thing that is really important to point out here is that whenever you change the value of an asset, you actually change something that is stored on disk. So if I now stop the simulation, we will see that the last value that I entered is still valid even though it was entered during the simulation, because we are actually modifying an asset on disk. It's not the same case as if you go here, you start the simulation. Now we have a running simulation and we change the mass to 1 and we press stop. Now all these settings are back to the previous value? That's because we're changing an instance in the scene. It's instantiated into the running scene. It's not an asset on disk. So let's have a look at the friction coefficient and what we can do with that. Here we have a scenario where we have a dynamic rigid body box standing on top of a rotated plane. So if we start the simulation, nothing happens because there's some friction keeping it from sliding. Now let's assign a shape material to this box. So now we have the same shape material on this large box and the small box. Let's also create a contact material, and we'll call this box contact material. And this contact material should define what happens when two shapes using the same material, the box shape material, collides. We also need to add this to the ContactMaterialManager. So we can go here, we can see that, yes, we actually have something now here called box contact material. So let's have a look at the friction coefficients. We can see that we have two of these. And the reason is that there is a primary friction direction and there is a secondary friction direction, and they are orthogonal to each other, just as we can see in the arrow here. By default, they are oriented along the world coordinate frame. So in Unity, it will be along X and along Z. Now, if I change this value into 0, nothing happens. But if I change this to 0, it starts to slide. And that's because this Y axis here is along this axis, and this X is along the green axis here. So now comes the question, what if I would like this friction direction to be along this local coordinate system? So if this box would be rotated in any way, then I would like it to slide along that axis. So if I now rotate the box, we stop the simulation, I rotate the box like this. Now I would like it to slide along this direction and not along this direction. So if I just start the simulation now and we do the same, we will see that it's not sliding along this red arrow here. Instead, it slides diagonally. And that's because the primary direction is still along the world coordinate system. So we have something here called is oriented. And if we check that box and we use this rigid body as a reference object, what happens then is that we have suddenly defined the primary direction to be along the green and the secondary to be along the red. And we can actually switch here to just to make sure that we get the correct axis. Now, if I would do the same thing now, I would start the simulation. Sorry, there's one more thing we have to do. We have to assign a friction model. And we'll talk more about the friction model just in a little bit, but we need to do that. So let's start the simulation and change the friction value in Y to 0. And now we should see the box sliding along that axis. Exactly what we wanted. And still, if I change the value in Z, well, then it starts to slide along that direction. So here we can use this is oriented for an instance of a contact material. Obviously, if you have several shapes using this box combination, they will use the same reference. So this is only to be used for specific purposes such as tires and things like that. Or there's also another alternative to use it together with our tracks model. If you want to learn more about friction, you can find the information in the user manual. Here you can see all the various friction models and all the solvers that are available for you as a user of AGX Dynamics for Unity. Let's open this friction model asset that I just created. By default, what you're going to see is that the solve type will be split and the type will be iterative projected friction. Now, when are you supposed to use the direct solver and when are you supposed to use the iterative solver? Well, that really depends on the scenario. In this case, what we're looking for is a dry frictional contacts between these grasping devices and this box here. And we cannot get dry friction using the split solver. The split solver is a mix between the direct and iterative solver, which give you robust stacking, but it will not give you the kind of dry friction that you need. So in this case, we have to switch to the direct solver. And if we do that, close it, open it, we can see that it's perfectly possible to get this. So we get very, very accurately simulated direct friction. Now, if I would switch to iterative, it will just start to slip. That's because the precision is not enough to solve this system. Now, you remember I said something about warm starting of contacts. There is a setting here in the AGX Unity simulation object that is called solver settings. So if I would create new solver settings like this, and I will double click that, we can see that we have something called warm starting direct contacts. If we enable that and also use the direct solver for friction like this, then it will actually be a lot faster. Because when we are already in contact like this, we can reuse the solver result from the previous time step to solve the next time step. So it will be much, much faster. So here's a scenario where you actually need the direct friction solver. Other scenarios might be to simulate tires. So you want to have really good grip between the terrain and tires. Then you should also use the direct friction solver. So when should we use the iterative solver then? Well, let's have a look at a different scenario. Here we have a large set of boxes and they can all collide with each other. We can see that this blue has a box shape material and all these boxes is also made of box shape material. So we need to find a contact material that defines the interaction between box shape material and box shape material. And here we have that. We also see that we have a friction model called box friction model. It's just a specific friction model for this combination. And if we open that, we can see that we're using the iterative solver. If we would first choose the split default contact friction solver, and in short, it basically solves the normal force with the direct solver, and then it uses an iterative solver for the friction. So you get a really robust stacking, but the friction is not as dry as you would get from a direct solver. But we can see now, if we run this, we get a statistic time of about 15-16 milliseconds, and most of it is spent inside of the solver, which is reasonable. Now, let's see what happens if I change it to the iterative solver. It goes down to 3 milliseconds. So it's much, much faster on this large stacking system. So typically, whenever you want to have large set of objects interacting with each other, you should use the iterative solver. And you can use the contact material and the friction model to define that kind of interaction. So by having all these options, you can set up your scenario exactly the way you want. If you want to use highly detailed gripper with really dry frictional contacts for robotics, you can do that. Or if you want to combine it with iterative solvers for large stacking systems, you can also do that. It's all sort of built into the system. When two objects overlap, we will get contacts. If one of the objects is a triangle mesh or both of them are triangle meshes, we'll get potentially a large set of contacts. So if we start this simulation, we can see that there's lots of contacts here being generated. Basically one between each triangle in the mesh and the box. So we can also see that we're spending a lot of time inside of the solver here. Now, one way of solving this is to use contact reduction. So here we have the contact material between the knight material and the box shape material. If we enable contact reduction, we can see that there we have a lot fewer contacts and we're only using 0.4 millisecond instead of 13 to solve the same system. We still get a robust set of contacts so that we have a stable object standing on top of this box. Now there is also a level of reduction,
And in most cases, moderate will be the best option. Using aggressive, well, you might get contacts, a too aggressive procedure where they remove too many contacts. So this is probably not what you want. So in most cases, I would say moderate is the level of contact reduction that you should use. The last parameter that we're going to discuss is YoungsModulus. YoungsModulus is used to define the stiffness when two objects collide. So first, let's assign a material to this sphere shape. And then we start the simulation and we'll see that it bounces perfectly. Let's now select the contact material that is being used between a box shape material, this ground, and this sphere. So we can see that we have a YoungsModulus here. Remember that YoungsModulus for steel is about 200 gigapascal. So that's a good reminder of what YoungsModulus can be. In this case, it's a lot less. What happens if I set it down to 10 to the power of 6? And then we'll see that it actually behaves like it's colliding with mud. And if I would reduce this even further, we see that it just sinks down. So we can use YoungsModulus to define the stiffness in any contact. So if you have a very heavy object, then you might have to increase your YoungsModulus quite dramatically. In this scene, we're actually using YoungsModulus to define the stiffness of the tire interacting with the box. So if we start the simulation here, we can see that we actually get some bounciness or some deformation here between the tire and the ground. And that's because we are using a slightly lower YoungsModulus value. Now, once again, if I reduce this more, we'll get sort of a very, very soft material. And we can increase this until we have a really stiff material if we want to. So we can use YoungsModulus to define the stiffness of the interaction between two objects. And that concludes this tutorial.